Welcome, everybody. This webinar is scheduled for an hour. I don't think the presentation is going to take an hour, but we want you to ask questions as we go along. This will not get into programming and things like this. This is strictly about hardware and where to wire the hardware, and we'll talk a little bit about various options for that kind of stuff as we go through here. But the goal here is to bring you up to speed on what's factory wired, what's field wired, and the options for you to do that. So without any further ado, we'll get going here and start off. So the product we're talking about is the Vitocal 100 AW AM2V air to water heat pump. This is a new product for Viessmann in North America. It is not the same heat pump as we sell in Europe. This is a North American designed product. Your basic system comes with the outdoor unit, indoor unit, and the buffer tank, and then the optional indirect tank we see on the right-hand side over here. So we're going to talk about all the interconnections between those devices and how to use them. So we're going to explain the overall electrical requirements between the indoor unit and the outdoor unit and the main supply. We're going to identify field wiring components and their terminations between indoor and outdoor unit and the buffer tank. And we're going to take a look at some of the optional third-party equipment and controls that you might use. This is going to be variable depending on whose equipment you're going to use, and so we're not going to be able to give you, a definitive yes or no on any particular thing because it's not our equipment, but we'll give you some guidelines on how to work those things. We're going to summarize the factory wired components. We're going to show you all the factory wired equipment, and we're going to talk about the wired components for the field as well, with things you're going to connect, and we're going to show some applications drawings so you get a handle on where we are trying to connect it to in relationship to a drawing or a particular installation. These are by far not the only ways to do these things. These are guidelines. There really is a field, judgment on how you hook things up and wire things up, but we're going to talk about the basics here. So we'll start with the outdoor unit. The outdoor unit is the air to water heat pump. Outdoor unit is a self-contained monoblock, so all the refrigeration and everything is outside, and it's converting refrigerant to glycol in the outdoor unit, and we're piping glycol. So we have to deal with all of the equipment that's inside the outdoor unit, so we can see the full load amps. As we get bigger compressors and more fans and things like that, we're going to have a higher amp load. We're going to give you some guidelines down here, maximum breaker, common breaker sizes, but you really are going to have to follow your local electrical code to hook those things up. So to access the wiring panel, just one panel on the side. If you're looking at the front of the unit, it's on the right-hand side. 2 screws pull that cover off, and inside that there are only 2 connections. You have the main power connection here, and you have the communication bus connection here. Everything else in this unit is already wired factory inside the panels that are in the top. So these are the only field terminations you're going to have to do. And like I said, you're going to have to follow your local electrical code, whether US or Canada or local state or provincial amendments to do the wiring of these things. So we're not going to be too specific on wire sizes and breaker sizes. That's a local electrical code determination. But what I want to emphasize is here, this is a 230 volt single phase device, and it requires line 1, line 2, and ground. You do not need a neutral for the outdoor unit, right? You just need line voltage and ground, and the outdoor unit does not need a neutral. I want to emphasize that, just save you guys a little bit of run around or a little bit of money, because I've seen where the guys will pull the 4 wire out there and go, oh, what? I don't have any place to put this. So no, there's no neutral required on this outdoor unit. The overall electrical drawing you get with the unit is kind of broken down into a few different areas. You have the outdoor unit wiring over here. You have the indoor unit wiring over here. You have the field connections down below. So these are all coming out of the unit to field devices, and there you can see the communication goes up and around. They're all labeled with nomenclature so you can see what's going on in different places. I'm going to zoom in a little bit closer on most of these drawings so you can see a little bit better on what we're talking about. But this is the wiring diagram that's going to come with the unit, and it is the one I'm looking at is for the small unit. Some of the components up here in the top of this drawing will change and move around a bit as we get into units with bigger compressors or double fans. But essentially everything in the main control wiring is all the same between all three units. So let's take a look at the the factory wired inputs. So there's a whole bunch of analog digital input series here, and we're going to walk through the important ones that you might want to need for troubleshooting. At AIDI 12, you have two limits in series here. The first one is the high pressure limit. This is the refrigerant high pressure, and it will shut off the outdoor unit compressor at a high pressure condition. The next one is in the series is the over temperature limit. Again, this is high temperature. We're going to look at protecting the unit from a higher temperature condition, and this is where the over temperature limit. So either of these limits will trigger based on this input 12. The next one over is a low pressure switch. So this is a low pressure limit switch, and it is going to shut the compressor off on a low refrigerant pressure. Again, this is a safety device, so it's going to be an open-close switch. You have the flow switch. Because the circulation in the outdoor unit comes from the indoor unit or a pump that's controlled by the indoor unit, we need to prove that there's flow within the outdoor unit before we want to start compressors and things like that. So the flow switch has a minimum flow requirement, and that is going to be what triggers when the flow switch closes. That means it sees flow from the indoor unit, and it's going to be able to run the outdoor unit's equipment. Then we have the low pressure sensor. This is a transducer. So this is an active sensor, not a switch. And what it is used is because we have variable speed compressors, variable speed fans, variable speed pumps. This input here feeds into the various control algorithms, and it will make the compressor, fans, pumps work at a proper speed to do the load we're trying to deal with. So this is a active sensor. It's not a switch. It's an active transducer which feeds information. Now you can read this information here. You can actually read all of these points here in the indoor unit's control display. So you don't have to worry too much about what is it doing actually on the outdoor unit. There's no display on the outdoor unit. Everything is fed through the communication bus to the indoor unit. So all the diagnostic will be easy to find in the indoor unit. And then we have a whole series of temperature sensors. So we've got inlet water, outlet water, coil temperature, ambient temperature, suction temperature, antifreeze temperature, the EVI gas temperature, the EVI gas out temperature, and exhaust temperature. So these are all thermistors, but you'll notice that these are not 10K thermistors that we would normally see in the Viessmann equipment, the indoor unit, as well as our boilers. All use 10K NTC thermistors. These are not all NTC, or they're not all 10K. They're NTC thermistors, but they're not 10K. So most of the temperature sensors are 5K thermistors, and the high temperature one is exhaust temperature is a 50K thermistor. All this really means is when you look at make sure you're on the right chart when you're trying to troubleshoot these. If you try to troubleshoot these sensors on a 10K chart, you're going to have a wrong reading. Basically, when we talk about 5K or 10K or 50K or whatever K it is, that is the nominal reading, the resistance across that sensor at a nominal reading, which is typically around 68 degrees Fahrenheit or 20 Celsius. And that's typically how they nomenclature all of these. But these are 5K at that temperature and 50K at that temperature as opposed to 10K at those temperatures. Okay, just so you understand that these are not the 10K sensors we're using just about everywhere else in the Viessmann world right now. So let's take a look at the indoor unit. The indoor unit consists of a main circuit board and a bunch of accessory equipment. So it has its own amp draw. So we have, again, a 208, 230 single phase device, and the two smaller units draw a 31 amp full load because they have 2 3 kilowatt heater elements, or 6 kilowatt total. But the larger unit has a third 3 kilowatt unit, so it's 9 kilowatts in total. So this is why we have the higher amperage of the larger unit. Again, we're giving you maximum breaker sizes, but you're going to follow your local electrical code to determine that. Those wires all come into the top mono connector block here. This is a Wago type connector block, so it's like a snap closed. When you pull this little yellow tab up, it'll come to a stop. Pull it up to the second stop. That will allow you to insert the wire in it and then push it right back down flat. We'll lock the wire in place. But you can see that we have a ground, line 2, line 1, and a neutral. So the indoor unit does require a neutral. So this is different than the outdoor unit, which we didn't need a neutral on. The indoor unit does require a neutral. Okay, so it's a 4-wire connection. Below that, you'll see 2 breakers, which are going to protect the system, the internal components from a high current condition. And again, follow your local electrical code. This is a 4-conductor system, where the outdoor is a 3-conductor system, but you have to follow either the NEC or the CEC in Canada to get the proper breaker size, proper wire size. You know, depending on what you're doing, whether you're running wire in conduit or whatever, it's going to be different, right? So you need to follow that local electrical code. So the other connection we talked about between the outdoor unit and the indoor unit is communication. So in the outdoor unit, we looked at this block here where we had power and we had the communication block next to it. In the indoor unit, it has a similar termination on the circuit board. And we see we have wiring between the indoor unit and the outdoor unit, which we say requires to be a 20 gauge paired twisted pair cable. So 20 gauge being the gauge of the wire. Personally, I would normally use 18 gauge myself, but this will work down to 20 gauge. I just find 18 gauge is easier to find. It's a pretty standard communication cable, but it's important that this is communication cable, not thermostat wire. Thermostat wire provides no electrical shielding for noise from inverters, drives, or variable speed fans or pumps. And we see this device has a few of those in all cases, right? So it's important that we use this twisted pair. The reason why these pairs are twisted, it provides some shielding already, preventing some RF noise from entering the cable communication bus. But the other part of this is the shield. Now, this wire comes in a couple different ways. This shows a foil shield with a shield conductor. There's also the type that is a braided. You'll have to unbraid the shield and then twist it together as the ground. Either one works. They're both the same, virtually the same isolation. The foil one probably has a little bit better shielding, but I don't think for what we're dealing with, it doesn't make any difference. So if you can, whatever you can get in the cable. And it's important that, again, we're going to run 2 cables and the shield. So I'll talk a little bit more about the shield as we look at this again. So again, indoor unit, outdoor unit, twisted pair cable. It is polarity sensitive, so make sure that the wires are polarity correct to the wiring diagram. And you can see that what we have here in the indoor unit, there is a block that has 4 connectors, but we're only using the 2. The one that's marked as slave, we are not using in this unit, but we are using the end of line termination resistor. This came in the package with the spare fuse on the indoor unit. So you're just going to want to put that across this AB connector. This is going to show the communication bus that this is the last device. It won't be looking for anything beyond this. And so we talk about it, call it end of line termination. And you notice that what I've done here is in this drawing is we've taken the shield, which is that grounded wire, and right above this connector in the panel, there's a ground screw. And that ground screw then will be a place where we can tie the shield in. So we're going to connect the grounded shield on the indoor unit. On the outdoor unit, you'll notice that I haven't shown a ground connector. That's because we do not want to ground the outdoor unit on the shield. We're going to tape it off so that it doesn't touch the cabinet or anything else around it, and just run the 2 conductors. If I was to ground both ends of this, it's a conduit. It doesn't provide me any RF shielding. If I ground one end, the shield becomes basically an antenna, and it will drain RF noise to ground. So this is why any shielded wire, doesn't matter where you're going to use shielded wire, and any application requires shielded wire, we're typically only going to ground at one end of the device, and usually there's on the device that's providing the communication bus, which is the indoor unit in this case. So there's our circuit board. It sits behind the main display, and it has a whole bunch of terminals. Some of them are factory wired, some of them are field wired, and we're going to take a look at the various options here. So all of these little connectors you see inside in the internal of the board, this inlet temperature, outlet temperature, these are all internal to the actual machine, so they are all factory wired. And we have a bunch of connectors on the right-hand side here. Some are factory wired and some are field wired. So when I look at the top, the factory wired, we have the power connector. So this is coming from the breaker system. The power comes in through the breakers and then to here. So we have line, neutral, and ground again. We have the electric heater element output to the electric heaters, and you'll see there's 3 here. But again, remember, these 2 smaller units are not using the 3rd heater element. We're only using the 2. The next one down is the internal pump. So this is the velo pump that's inside the indoor unit, which is the normally carrying circulation between the outdoor unit and the buffer tank. And it has its power here, but down at the very bottom is the pulse wave modulation speed control. So there are 2 connectors on that pump. One comes from the speed control, one comes from the main power of the pump. And this will be very similar to what we have in our Viessmann 100 and 200 current generation E-series boilers, where we have a variable speed pump. There is a power connector, and then there's a variable speed control connector. Down below that, we have an output called diverter valve, and it is going to be the wiring that's factory connected to the internal diverter valve, which will switch from domestic hot water to heating. So when there's a domestic hot water calls, this valve is going to travel to the domestic side. If there's no domestic hot water call, it's going to travel to the heating or cooling side, and it's going to be automatically going to happen. And we talked a little bit in a previous training about how you can do an override on the valve manually, but it's always going to be electrically connected here. The next one down is the heater shutdown. This is a safety limit that's connected to the top of the electric element heat exchanger. And it is a automatic reset limit. And if the water temperature gets to the reset limit set point, it will open up and shut off the electric heater elements. It doesn't shut off anything else. There is a manual reset high limit, which we looked at in previous training, which shuts off everything, right? So it will shut off the whole unit, and it is manual reset. But this is the automatic reset limit that's attached to protect the heater element heat exchanger. Now, one of the things that we will look at, we'll talk about later, as an accessory boiler possibly being used. And in that case, what you have is that it will ignore this limit when the accessory boiler is enabled. And we'll talk more about that when we get into programming and things in future presentations. Okay, so those are all the factory wired connectors on this side. There are 3 connectors that are field wired. The first one being the relay output to that accessory boiler. Remember, we talked a minute ago about the accessory boiler, and we're going to say, if my heat pump and my electric backup in my heat pump does not have enough power, enough BTUs to satisfy 100% of my building load on a design day, we may want to add an accessory boiler. That accessory boiler then will get a start command from here. We're not telling the boiler what to do with that. We're just saying, hey, make heat. And when we enable this point, it's going to disable the electric elements, and it's going to disable the heat pump. And then the external boiler will do all of the work in the heating of the building after that. So just as an example, using a Viessmann 100 boiler as an example, we can see that the connection from the output of the IDU to the 96 input on the Viessmann 100 boiler, that will give that boiler a call for heat. The set point is set in this boiler. It's not set anywhere else. You're going to set the set point in this boiler. This indoor unit is not going to tell the boiler what temperature to go to. That's going to have to be set. And you're going to remember that by the time this boiler is enabled, it's cold outside, right? So you probably don't need to do outdoor reset on this. Plus, you also have to remember that this is also going to be doing your domestic hot water energy production. So you probably want to have it set for the highest of whatever those 2 values are in your settings. So again, it's from the output here, dry contact closes this, the boiler starts. The boiler has an internal pump. Well, we're going to use this heating circuit output pump as an optional device here. So you see it's connected to this diverter valve, which we see here. And the whole point of this diverter valve is that when I'm making heat from this boiler, why would I want to send that heat out to the outdoor unit and back when I'm not actually using that energy out there? I'm not producing, I'm not accessorizing, I'm not adding anything to it. So we can use this valve then basically to, whenever that 96 contact closes and the what would normally be a pump to start. It would drive this valve to close this path and open this path to allow the water to circulate through the system continuously, but not send that conditioned water to the outdoor unit, which is going to be set in very cold outdoor temperatures and not providing any energy to add to the system. Again, this is an option, probably recommended by, I would say by myself, I would recommend it, but it is not something that you have to do. Again, it's something that we look at from an application perspective, saying in your application, maybe it's a good idea to consider this. The other two connectors that are on this indoor unit, there are two. One has a factory jumper on it, FN1. So from the factory, FN1 has a jumper on it, which means this heat pump is ready to make heat, right? It is not enabled to make cooling until I close the contact on FN2. So this is normally a field supplied jumper. If you're going to have just a heating only heat pump, you don't have to do anything with it. If you're going to have a heating cooling heat pump, where you're going to say run chilled water through a radiant cool system or a fan coil, then you'll need to close this contact or none of your cooling functions will operate. You could use a field device to turn these on and off, maybe a utility device or something like that. But remember that these are not thermostats. This is not a call for heat or a call for cooling. This is a enable cooling or enable heating. We're not going to be using this as an open close contact from a, say, multi-zone control to turn the cooling on or turn the heating on or whatever like that. We want to isolate the field devices from the heat pump system so that we control the buffer tank temperature and the DHW temperature. So in 99% of your cases, you're going to see it with just jumpers on it. So if you want cooling, you need to install this jumper across FN2. Now, the other side of this unit has the field connections, and all of these connections are going to be field wired. So the unit's going to come with a certain amount of sensors and things like that, and you're going to connect field devices and pumps and valves and things like that. So let's take a look at a little bit closer to what those things are. Over here, we have a whole bunch of temperature sensors. Outdoor sensor, room temperature. This is like an optional sensor. We don't have to use a room temperature sensor, but you can. DHW, heat cool circuit 1, heat cool circuit 2, temperature sensors. These are all standard NTC 10K sensors. So these come with the unit, or you can get the accessory. We'll talk a little bit later about optional accessory sensors for additional immersion sensors and things like that. There's my communication bus between the outdoor unit, the indoor unit here, and see that where I told you there that slave, there's nothing connected to that. And then we have the mixing valve for circuit 2. Now this is set up and programmed and ready to go for a Viessmann 120 volt mixing valve. If you are going to use somebody else's mixing valve, you will have to understand that you may have to change the timing in coding. And again, coding we'll talk about in a future presentation when we get into the various programming and things like that. But this is right now, this is coded for the stroke time of the Viessmann actuators, right? So it's important that we make sure that that is how we're going to look at that. Then we have the heat cool circuit 2 pump, the heat cool circuit 1 pump. We have the glycol pump, and I'll talk about this in an example. This is a pump where, for either one or two reasons, we're going to say we don't want glycol running through the whole building, so we're going to put a heat exchanger to isolate it. We can use this pump to become the primary pump between the heat exchanger and the outdoor unit. Or in the case of a really long piping run between indoor and outdoor unit where the indoor pump might not have enough oomph to get to do the work, we can again put out something like a low loss header, closely spaced tees, and this becomes the primary pump. So we may or may not use this pump depending on the installation. And then we have a DHW recirc pump. The DHW recirc pump obviously is for DHW recirc, and with the idea here is that if it's connected to our indoor unit, you can put a schedule on it, so you can run it through schedule. The other device I kind of skipped over here is that heating cooling valve. Now, again, we can use this to block hot water or block chilled water, depending on how we wire it. I would say in 99% of your cases, if you're going to use it, you're going to block chilled water from going to, say, a radiant floor heating system. But we'll show you a couple examples here. In the application of this, where we're blocking cold water from getting into the radiant floor system, this valve will then, when the dial on this front of the control is set for heat, so you see the heating icon is eliminated, it will drive this valve so that path of water can go through here. and it will circulate through the system like this. Now, this could be a two-way or a three-way valve. I'm showing it both ways and both wiring configuration. This one here is powered open, powered closed. This is powered open, spring return, but either a two or three-way valve could be either way. I prefer to use the three-way valve here, and the reason why that is that if there's ever a scenario where this pump is going to run either manually through a relay test or automatically through an exercising or something like that, then we do not want this pump to run into a dead head. So we're going to have a valve that's closed here, and so the pump is going to basically run into a dead head. It has no place to go. So this, the idea of the three-way valve is it gives it a path this way during the times when it's in cooling mode, and the system's in cooling mode. Now, like I said, we could use it as a cooling block, and now maybe this air handler is strictly cooling. We're not doing any heating in this air handler. Our head office in Waterloo, not the same, but kind of a similar system where we have boiler heating radiant floor, and the whole building is radiant floor. But in certain parts of the original building, we have a chiller and chilled water coils. So those coils in the ductwork, they're just doing air conditioning. They're never doing heating. So, and this might be an air handler that's doing the same thing. So to prevent the hot water from getting to it, we would wire it to the cooling contact, and then this valve would close whenever it's in heating mode and pass water through it when it's in cooling mode. The unit came with 4 temperature sensors, and a outdoor sensor, a room sensor, 1 immersion sensor, and 1 10K strap-on sensor. The idea of the strap-on sensor is for heating circuit 1, and we look at most of the drawings that I'm going to show you we're using the heating circuit 1 sensor in the buffer tank. So it may be you want to get an optional second sensor, the immersion sensor that you can buy as an accessory to make that work that way. But I'll show you a couple of different ways we're going to do that. Okay, so the mixing valve kit is going to be a Viessmann part number, which is going to come with the motor, and it's going to come with the temperature sensor, and you're going to option the valve body as a separate part. And to wire this, you just have a strap-on sensor here. It's a 10K, again, a 10K standard NTC thermistor, wires back to the temperature input of number 2, and the motor is connected to the 120-volt circuit from heat-cool circuit 2 to drive that valve. The way it's wired is we have line, neutral, line on the motor, and we have line, neutral here on the plug. So we're going to do it this way. And the reason why we can do it this way is if it's a 3-way valve as an example, and you pipe it in, and it might be great, and the electrician comes and wires it, and you realize that the stroke is going the opposite direction just because of the way it was installed. You can simply take this plug off of this, unplug it, rotate it 180 degrees, and that will change the rotation. That makes it very easy to fix a problem with a valve that maybe didn't get put in exactly the way the drawing does, or the electrician that didn't understand the idea of open and close on the valve. He's strictly wiring it. So this is why we show in the drawing, we show it this way, because this plug then can be flipped over. There's our 10K thermistor, the optional part number if you wanted to order a second 10K thermistor to make, because you're not using the HC1 as a strap-on, you can get a second optional 10K sensor. And when we look at the strap-on sensor, like I said, it comes back to this X18 connector THC2, and it is not polarity sensitive. It doesn't matter which way this works. It works both ways. And it would be the same with the immersion sensor. You just wired to 3 and 4 here. Now, when we have the optional indirect tank, there will be some wiring that it has to be done for that. And some of it is independent of the indoor unit or outdoor unit. And maybe there will be a connector to the indoor unit. So the heat pump indirect tanks will come with this electronic thermistor, not thermistor, anode. And the anode will provide protection to this tank with an active anode device. It's not a passive device like our magnesium or aluminum anodes we see in most of our glass line tanks. This is an active sensor, so it has to be wired. So you will get the tank, and the anode will come in a little box with it. And there's a little knockout here at the top in the plastic that you'll take out and remove some of this insulation. And then there are two little dimples in the jacket where you can screw the indoor or the anode controller to it. And then you're going to take the wire from the anode unit and run it in through that little hole. And you're going to terminate it on here. Now you should not be able to terminate this backwards because the connectors are different sizes. But I'm never going to say nobody can ever do it. Somebody might be able to figure out a way to do it wrong. It's important that you just do it the way it's supposed to be done, because an electronic anode hooked up backwards will actually eat the tank. So I'm not trying to be a fearmonger here. Just as long as you do it the way it's naturally going to be done and don't start cutting connectors and put new connectors on, you'll be okay. Okay. And once you've got that there, then we have to power this device. So then there's a 120 volt cord, about six feet with a U-ground plug on it, plugs into a receptacle, and that will provide protection for the tank. The tank will have some LED indication to tell you that it's working or not working. And that will provide the protection for corrosion on the glass line tanks that are designed for these heat pumps. So let's take a look at some system examples and put that wiring we just talked about together in kind of a piece here. This is a full drawing. This shows everything that this heat pump can do as far as electrical connections. So we have the outdoor unit and the indoor unit communicating here through the communication bus. We have an outdoor air temperature sensor that's going back to the indoor unit, right? We're not showing the power connections here. We got power connections here and here. We have a connection to drive this valve from this boiler. Remember, this is the accessory boiler and that three-way valve to here. Now in this drawing, we're showing a low loss header, but this could be a plate exchanger if you wanted to isolate the glycol. In this case here, we're just saying, what if the piping run is long? And again, that pump is controlled by the indoor unit. Anytime this pump starts, that pump starts. So it'll be a working together as a team. Then the indoor unit can also control the domestic hot water recirc pump. The indoor unit takes the input from the tank sensor. The indoor unit takes the heat circuit 1 or heat cool circuit 1 sensor, which we're normally going to put in the buffer tank. And I'll show you a couple of options of that in a second. But the idea here is that measuring that temperature in the buffer tank will make the buffer tank maintain at the circuit 1 temperature all the time, whether it's chilled water or hot water. And then we have an optional room temperature sensor here. And we have this valve here. This is this heat cool isolation valve. All right. The pump on the air handler, in this case here, is run by the air handler, and the thermostat is controlled to the air handler. And again, this doesn't have to talk to the indoor unit at all. It's really just saying, hey, I have a call for energy, and I'm going to pull that energy from the buffer tank. So there's no electrical connection between these two devices. We do have a pump connection for this. These essentially both are heating circuit 1 or heat cool circuit 1. And we have the air handler, which can maybe do hot water, chilled water. And this is going to run anytime there's a call. So again, this is why it's important to have this valve here to prevent chilled water from going into these panel rads or into the radiant floor system. And then we have the circuit 2, which we have the motor for the mixing valve. We have the pump with the temperature sensor. So this shows you all of the potential electrical connections between indoor and outdoor unit and field devices, as well as the main power input. Now, I talked a little bit about optional places for the buffer tank sensor. Because the unit comes with a strap-on sensor, you could strap it on to the return pipe. This is the water coming back out of the buffer tank out to the indoor unit, okay? And this would be measuring water temperature leaving the buffer tank. This sensor needs to be as close as possible to the tank, so it makes the most accurate temperature sensing. But anytime that the boiler is, let's say, producing domestic hot water and the circulation of the water is going through here, there's going to be no flow here. So it's not going to be able to read that temperature of the actual tank during those conditions. And we could still be drawing energy off this tank for an air handler. Let's say it's doing chilled water while the air heat pump is making hot water for the tank. So this is why I'm suggesting this is not the best place to put this sensor, but if you're going to use the strap-on sensor we send with the unit, that's what you're going to do with it. You're going to put it there. Again, you could get the optional immersion sensor, and that immersion sensor then would go into the buffer tank, give us a more accurate reading of the buffer tank. So when it switches back, let's say from domestic hot water to chilled water, and as an example, it already knows what the water temperature is, and the heat pump can load up more efficiently. Now, a simple system, no domestic hot water. So we have an air handler, hot water, cold water. We have the buffer tank, which is going to maintain at, depending on where we set the dial, if we set the dial for heating, it's going to maintain hot water. If you set this dial for cooling, it's going to maintain cool water, and it's going to maintain that all the time. And the air handler is going to start this pump as it needs to and draw off it. And when this temperature goes out of the set point, the unit's going to say, hey, Mr. Heat Pump, kick in. And sometimes it's going to pick up the electric heat on the indoor unit as well, depending on what your settings are for bivalent points. So this is a very simple system without domestic hot water. As soon as we add a backup boiler, because we have no domestic hot water, we could put the backup boiler right on the buffer tank. If we have domestic hot water, this doesn't work because when it's here, it can't do domestic hot water. But this is one optional positioning. And then as soon as we add domestic hot water, or in any other application we're going to show you, we put the backup boiler here, which gives us the ability to circulate water to the buffer tank or to the indirect tank, which we'll show here in this drawing. So we have one circuit here, one heat cool circuit. Now in this one here, we have one heat cool circuit with an electric backup boiler. Again, this is going to trigger the boiler below that cold ambient changeover point, adjustable set point. And then it's going to maintain, this is hot water, and this is hot water based on the set point in this boiler. Now, what if we take two circuits? So now I have an unmixed circuit and I have a mixed circuit. So this unit can do one of each, right? So this is my unmixed heat cool, and this is my mixed heat cool. Now, in most cases, we're going to do heat only here, but there are certain areas of North America where we could do radiant floor cooling. So that would be an application where we would see that, which is why I'm not showing that isolation valve here. And again, same scenario where we add two circuits, but we add the backup boiler because at a certain ambient condition, wherever this is installed, the heat pump and the electric heat isn't enough capacity to do 100% of the heating load of the building. So the backup boiler is sized to do that 100% load. And when it's enabled, the electric heat in the indoor unit and the outdoor unit here do not provide any heating. And this is, we showed this earlier. Now these is both two are essentially heat circuit one, but we're going to isolate this loop here from the chilled water side. So in the summertime, this gets hot or cold, and or cold water in the summertime, hot water in the wintertime. And this is only going to get hot water in the wintertime. This is only going to get hot water in the wintertime because this valve is going to prevent the water from going that direction. And there I show it with the plate exchanger. So again, we showed it with a low loss header before. Why would we want to do this? Maybe they don't want glycol in the whole building. This exchanger. One of the things you have to understand with this, though, is you're going to have to take into consideration that there is some efficiency loss through the heat exchanger, and you're driving one more electrical pump. So you have to decide whether that is valuable to your installation. And the same thing with a low loss header instead, because this piping range between here and here was very long. Again, showing it with the strap-on sensor. Here we have here a couple of QR codes which you can link to the Pro Toolbox, which is where all of these apps and documentation, Falco checker, and things like that are. That's about as far as I'm going to go today. Do we have any questions, Drew? How long can the communication cable run between the IDU and the ODU? Much longer than you'll want to run piping. It's probably go a couple 100 feet with it. I would think at least a couple 100 feet, and you're not going to want your indoor unit, outdoor unit 200 feet apart. So that is not a problem you're going to have an issue with. It's a standard Modbus. So if you're familiar at all with communication in a building automation system using Modbus, it's the same protocol. Will the outdoor temperature sensor accept a simulated signal from a third-party device? That's an interesting comment. You would have to simulate the 10K range. I know I have done that in building control systems where you take a control signal through a voltage divider, whatever, but it's not native to do that, right? You'd have to be able to, your output of your third-party device will need to simulate the resistance across the sensor at those temperatures. And it's a little harder to do than you might think. It's basically a, say a 0 to 10 signal that triggers a electronic decade box kind of thing. But it is possible. Yes, you could do it if you are sharp enough on building controls and building a device to do that, you could do that. But it's not native to do that. It's looking for a resistance across the thermistor.
So possible, but a little more complicated.
Yeah, I mean, it can be done, but you have to kind of guess, is it really worth it? I mean, you're talking, if I was to build it myself, it'd be a $200 device I'm building, right? And is there a value to that? Maybe even more than that.
Yeah.
I haven't built one for a long time. All right. Well.
Okay. Well, thank you
think we're
everybody
all
for
good.
attending today.
Yeah, and enjoy the rest of your day. Thank you, Drew, for backing me up.
No problem. Great job, Mark.
And we will see you next. Oh yeah, thank you very much. And we will see you guys next time. Take care.
Have a nice day, everybody.